So now that we have the solutions to rotational motion for one particle, let's imagine that we have a diatomic molecule. And unlike for our vibrational motion, we're going to actually connect those two atoms in our diatomic with a rigid rod. So this cannot change length. So it's rigid. That's why it's called a rigid rotor. So it can't change length, so it always has the length of r, the distance between the two particles. And what we're going to do is ask ourselves what happens when this diatomic molecule rotates in space. So let's look at the rotational motion of a diatomic. So the first thing to notice is that this freely rotating diatomic has no forces acting on it. And so the potential energy for this system is zero. And so the Hamiltonian that we need to solve is just going to be the kinetic energy Hamiltonian. And remember that for rotational motion, this is going to be L squared over 2I. And the moment of inertia for a diatomic molecule, for two particles connected, is the reduced mass times the distance squared between those particles. And so the Hamiltonian that I need to solve is equal to 1 over 2 mu r squared, and then I need my L hat squared operator operating on psi, theta, and phi. So I need both theta and phi because my particle can rotate along either one of those angles. But lucky for us, we already know the answer to L hat psi at theta and phi because we know that the solutions to this are the spherical harmonics. And the eigenfunctions for L hat z are going to be the angular momentum quantum number, and in this case we're going to use J rather than L to denote the fact that we have a multi-particle, a two-particle system rather than a one-particle system, times my h bar squared times my psi back again. And so the kinetic energy operating on that same function is just J times J plus 1 h bar squared over 2I, and then my wave function back again. And so I can see that my energies for the rigid rotor depend on this quantum number J, and the energies are equal to J times J plus 1 h bar squared over 2I, where J can be 0, 1, 2, 3, etc. It's customary to write these energies in terms of h and not h bar. So if I do that, I have J times J plus 1, and then I remember that h bar is h over 2 pi, so I have that squared divided by 2I. And so that gives me J times J plus 1, h squared over 8 pi squared times I. And we typically equate h squared over 8 pi squared times the moment of inertia with something that we call the rotational constant, or B sub e. So with that definition, we can write that the energy of any J level is equal to J times J plus 1 times B. Remember that each of these energy levels is degenerate according to what the m sub j values can be. And m sub j values can range from minus j in integer steps up to 0 and then up to plus j. So each of these levels is 2j plus 1 degenerate, because there are different ways that angular momentum vector can point for each of the different energy levels. So we have that the energy of a J level is equal to J times J plus 1 times B sub E, where B sub E is a constant that depends on the particular diatomic we're talking about. It's h squared over 8 pi squared times the moment of inertia. And the moment of inertia of that diatomic is its reduced mass times the square of the equilibrium bond distance between the two atoms. So this moment of inertia is different for each diatomic, which makes B different for each diatomic as well. So if we look what the energy levels look like, so if we draw out the energy levels, we can see that at J equals 0, we have an energy of 0. And at J equals 1, we have an energy of 2B sub E. And then when we have an energy level of J equals 2, then we have 2 plus 1 is 3 times 2 is 6. And so we have 6B sub E. And so we can see that the spacing between my energy levels is going to get larger and larger as I go up. So the next one that I have is J equals 3. So 3 plus 1 is 4 times 3 is 12. So now we're all the way up here. So my levels get further and further spaced apart as I go up. So the difference between any two energy levels, why do I care about that? I care about that because if I want to excite a rotation, if I want to get the molecule rotating faster, so if I want it to get it rotating faster, I have to go from one quantum level to a higher quantum level, one with a larger energy, so it's rotating faster. And to do that, I have to absorb a photon that has an energy that matches the energy gap between the two levels. So if I look at in general, at my energy gap between J and J plus 1, I will find that I have, my final state is J plus 1 times J plus 1 plus 1 is J plus 2 times B sub E minus my initial state, which is J times J plus 1 B sub E, and that is equal to J squared plus 3J plus 2 times B sub E minus J squared plus J times B sub E. And so I can see that J squared B sub E is going to subtract out, and I'll have a 3J B sub E minus a J B sub E, and so that'll leave me with 2J plus 2 times B sub E, or my delta E from J to J plus 1 is equal to 2 times the quantity J plus 1 times B sub E. So that's my difference between any two energy levels, and you can see that as it depends on J, so as J increases, that difference gets bigger. So a photon that could make this transition happen will have energy of h nu, and that energy has to equal the energy gap between the two levels. So the frequency of a photon that would allow me to make this transition would be 2 times J plus 1 times B sub E over H. So if I look at the microwave spectrum of HCl as a gas, it looks like this picture right here. So you'll notice that the separation between each of these peaks is 2 times B. So let's think about why that's the case. Each of these peaks comes from a photon being absorbed that has a frequency of 2 j plus 1 b over h. So I can assign a j value to each one of these peaks. So the lowest energy peak, the lowest frequency peak, is going to be for j equals 0. And when j is equal to 0, my frequency will be 2b over h. So if I assign this peak to j equals 0, then this frequency is 2b over h. And then my next one will be from molecules that are starting in j equals 1 and going to j equals 2. So if j is equal to 1, 1 plus 2 is 2 times 2 is 4. So if this is my j equals 1 peak, then this frequency is 4b over h. And then when j is equal to 2, when I start out in j equals 2, I get a frequency of 2 plus 1 is equal to 3 times 2 is 6b over h. And so you can see that the difference between any of these frequencies is 2b. So if I can measure the difference between peaks, then I can get a measure of 2 times b within factors of 1 over h bar. So I can calculate a value for b from the spectrum. And if I have a value for b, remember that b is equal to h squared over 8 pi squared times mu r squared. So I know my reduced mass for this molecule. I know what h squared is, I know what 8 is, I know what pi squared is, which allows me to calculate r for the molecule, which is the equilibrium bond distance. So I can get from these microwave spectra the equilibrium bond distance for different diatomics. So there's another really interesting feature of this spectrum. Notice that the intensity of the peaks follows this envelope. And you've seen that function before. That is exactly the Boltzmann distribution for rotational states. So remember that the probability of any J state being occupied, right, is the degeneracy 2J plus 1 times E raised to the minus energy at the jth level divided by K Boltzmann T all over the partition function for rotational motion. And so because the degeneracy increases as J increases, but the probability of the exponential unnormalized probability of populating that level decreases, we end up with a J level, so in this case J equals 3, that has a maximum population. And so if we have lots of molecules that start out in J equals 3 relative to J equals 2, J equals 1, or J equals 0, then if most of the molecules are starting here, there will be a lot of molecules that can transition to J equals 4, giving this J equals 3 peak a higher intensity than J equals 2 because I have less molecules in J equals 2 that can make it up to J equals 3, and even less in J equals 1 that can make it to J equals 2, and even less in J equals 0 that can make it to J equals 1. So the intensity of the lines tells me how many particles relatively are starting in that particular J level, so how many are there that can absorb a photon to go to the next level.